Hi, welcome to the Calculus 1 lecture series. And we are in the video number 3 here and doing the chapter 3 practice test review. And this practice test is to try to review our unit number 2 topics, the derivative formulas and the rules and applications. Okay, so we did the first 2 videos. So we covered I think 6 problems, and then this last video, we're going to cover the remaining 3 problems from this practice test here. Okay, let's go ahead and take a look at our practice test here. Okay, so we finished the number 6 here. Okay, so it's a number 7 here. Okay, so the number 7 here. So the first problem is, let's take a look. The Cobalt 60 has a half-life of 5.24 years. So I want to find the mass that remains from 100 milligram sample after 20 years. Okay, so this is the, like we talk about, we have like a half-life and the, the double life, right? So we all start with this equation. We say it's YT is equal to the Y initial and the E, the KTs here, correct? And now the YTs here, right? So now it's a half-life. That means whatever you started here, then this will be half of the Y0, right? So here, then the E, the KTs here. So now you can kind of, you say, okay, so I can cancel this Y0. And then what is here? So you will have, this is the 1/2 equal to the E, K, and what is the T's here? Is it takes 5.24 years, right? So now the things here, what I need to do is I need to solve this rate, right? So this is, we call this the exponential decay or exponential growth. So how do I do that? I will take the natural log of both sides. So this is natural log of 1/2. And because it's natural log and then E, they are inverse function. So what I have here is a K times 5 point what? 5.24. So my rate here will be 5.24 and the natural log of 1/2. All right. Okay, so now that's why I can put it back to my equation. So it's YT is equal to Y0 and the E, K is the natural log 1/2 and the 5.24 and the T here. Okay, so now I'm going to do a little bit, do a little algebra here. So this is, so take a look here, right? So this is a T over 5.24 and the natural log 1/2, right? So I know by the log function law, I can put this back to what? Back to the exponents, correct? Okay, so then let's take a look at what I have here. So this is the Y0s here, right? And then you put this back. So this is natural log 1/2. And then here, this is the T 5.24. Correct? All right, so now I see here, I said, hey, the natural log and the E, now they are the inverse function. I can cancel that out. And so in here, we say this is the Y0. Then here, this is the 1/2 T 5.24. That's right. So now this is the formula we're going to use. Like I said, if you remember that this is the half-life, right? So the same way, if you want to do the double life, so if you can remember, you don't need to derive this. So the double life will just be what? Will just be the 2's, right? So it's the same thing. So here is a T, from whatever the T0 give you the double life. So like in here, 5.24 give you the half-life. So you can directly, so it's not a Y0 equal to, so it's Y0 times, right? So here, so this is the So this is y0, that is the initial values of the yt's here. All right, so you can just directly use this formula here, or you can derive it. So this is our formula for the half-life. Okay, so now in here they said, okay, what is A here? They said find the mass remaining. So right now my initial, I have 100 milligram after 20 years. Okay, so that means I'm looking for how much I have left for the 20 years. So my initials here is 100, and this is 1/2, right? So T is what here? 20 years, and divided by 5.24. And then you can put it into your calculator, and you will get an answer very close to the 7.1 milligram. Okay, so after the 20 years, then the initial 100 milligram sample will have 7.1. Okay, so now let's take a look at part B. See here, part B, they say how long it will take the mass to decay to 1 milligram. All right, so that means here the YT is 1 milligram. It starts with 100 milligram, and this is a half-life, so it's 1/2. I'm looking for this T, right? So this is a 5.24. Then, okay, so now I would say this one is 1/100 is equal to the 1/2, and the T 5.24. So how to solve it? Take the natural log of both sides, right? So it's 1/100 is equal to the natural log. This is 1/2 T of 5.24. Then we can use this good property about the natural log against, right? So this is the exponents. We can move it to what? We can move it to the front here. Cool. All right, so I can see here, so this is going to be T over 5.24 natural log of 1/2. So what is the T going to be? So the T going to be 5.24 times the natural log of 1/100 divided by natural log of 1/2. So if you put it into your calculator, you will get the T is approximately to the 34.8 years. Okay, so this is like the, so this problem is what we call is exponential decay or is exponential growth, right? So the two typical problem we do is the half-life and the double life. Like I said, if you can remember this formula, you can just put the 1/2 in here, and if double life, you just put the 2's here. It can save you some of this, the how do you derive it, okay? Okay, so the next problems here, let's take a look here. The next province here is water. Okay, so water skier skis over the ramp. Here, this one is interesting. All right, and these ramps here, the height is 4 and the length is 15 feet. And they, when he come at the speed 30 feet per second. Okay, so we want to see how fast is she arrives as she leaves the ramp. Okay, that means he leaves the ramps here. Okay, so remember when we do those related rate problems, right? So what we did in our lecture, we said let's do a picture. So this one they already give us a pretty good picture, but now let's try to put this nice picture into some of the one we can work on. All right. Okay, so we have this right triangles here. That's pretty good, right? So we say here, and this is the given. This is 15, right? So this is 4. Okay. Then when this girl go up here, right? So this girl go up here. So basically, like in here we go boom, 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 boom. Let's say here, right? So this is the Z, right? So if this is the Z, and then what is here? This is the what? This is I call it is Y here. That is how high is here. right? Okay, now let's take a look here. So what do we have? What we are looking for here, okay? So now in here, let's take a look here. So we know the number 2's here. Let's try to list all the things known and unknown. So I know the dz dt's here, right? So the dz dt is how fast it's going. So it's what here is 30 feet, right, per seconds here. All right, and now what I'm looking for, if this is the, if this is the y here, right? So if this is the y, this is the height, right? So I want to see how fast I leave the ramp. So I want to find the dy dt, right? So this is what I'm looking for. See here, I'm going to find. So remember that, when we see this, so what did we see here? How we see is a triangle. See here, we always, so we have this small triangle, right? We did several of those type of the problem during our lecture series, and this is my big triangle. See here. Now I use the triangle similarities, right? If this is 4, this is 15. So let's take a look. So what is this bigger distance here? So this is 16 plus what? 16 plus Pythagorean theorem, right? 225. So what is this one will be equal to 16 plus 225? It will be 241, right? Okay, so the 241. So I know this distance based on the Pythagorean series 241 here. Okay, so now based on this one, let's try to relate it because the y and the z here. So I know y ratio of this small triangle y to z is equal to my big triangle is what? Is 4 to what? Square roots of what? 241 here. All right. So now I can get y, the relation of y is equal to the 4 over square roots of the 241 times what? Times z here. Okay. So now, so y and z, I finally have a relation. So now I will say the dy dt, how fast I'm leaping the ramp here, right? So it will be equal to 4 the square roots of the 241 times dz dt, correct? And I know my dz dt is what? Is 30 feet, right? So this is 241 times what? Times 30, right? So I will have, this is 120 to 41. Okay, so that's what approximately give me 7.7 feet per second. That means when I leave the ramp here, so at this point, my speed, this lady's speed is only going to be 7.7 feet per second, right? When she, when she leaves the ramps here. So this is a kind of a very easy type of the related rate problem. And so the only things here, like I mentioned before, use those similar triangles technique is very, very classical skill. You need to apply it frequently in the related rates problems here. So, for here, if you can see that, then you will be able to find the answer pretty easy, right? Okay, so now let's take a look this one here. So the last problem here, let's say here, they said a window has a shape of a, of a shape of a square and surmounted by a semicircle. All right. So base of the window is measured to have width. The base of the window measure have width 60 centimeter with a possible error of the 0.1 centimeters here. Okay, so now I want to use the differential to estimate the maximum possible errors, like computing the area of the windows here. Okay, so let's, like we did before, let's do a pictures here, right? So let's see what does that means here. So this is the, right? So here have a half circle, and this is the square, right? So let's say here, so this is x, and x here, right? So then because this is a semicircle, so this is a radius, right? So what is the radius here? It's x over what? X over 2 here, right? So I know the radius is equal to the x over 2. And let's say the, the window sit on a base is 60 centimeters, right? So that means the x is the 60s, right? And but I have a measurement error is 0.1. That means the dx is equal to what? 0.1 centimeter. So that means you can measure the 60.1 or 59.9 here. Okay, so now I want to find the maximum possible errors, right? So first, let's take a look at the area. So the area of this windows here, so will be the square. So what is here is x squared, correct? And plus pi r squared, right? So it's pi, what is the r? X over 2, right? Pi r squared is a circle, but I only have a half of the circle. So what I need to do here, divide by 1/2 here. So I will have this is x squared plus, I think it's a pi over x squared, right? Now I'm going to find the maximum error. So that means I'm looking for the DAs, right? So there could be the differences here. So here, what is here? This is 2x dx plus pi over a times 2x dx, right? Okay, now I can just plug the value. So what is the x here? So this is 2 times 60. And the dx here is 0.1. Then plus pi over a times 2 times 60 times what? 0.1 here. All right. Okay, so now if you put in this into the calculator, you will get this will be 16.7 centimeters square. That means the maximum error for the whole this windows here, right? So this window include a half circle and also include these squares, right? That means these windows, the real area could vary no more than 16 plus 7. So the true values here is will be 60 times 60 plus pi r squared. That's the true area. But then with the measurement error, it could be your true area plus minus 16.7, right? So this is the maximum error, for this window due to the measurement gauges errors here. All right, that's it. That is for the our unit about the derivatives, about all the different formulas and the applications. And I think this practice test will help you to review all this concept and put all of them together for you. Okay, and that's it. And hopefully you find that those 3 videos are helpful for you to review this practice test. All right, nice talk to you and looking forward to start another new unit here, our next unit. All right, okay, bye.